Hello everyone, welcome to 369 Chemistry, and in this video we are going to talk about your tetrahedral complexes, how splitting takes place in your tetrahedral complexes. So if you have clicked on this video, so I can imagine that up till now you know what is crystal field splitting, okay, what is the energy and everything. So we have discussed in the octahedral splitting in the last video, so you can go through that. So if you have come to this video, we will start with the topic of your tetrahedral complex. So we know coordination compound, they form complexes, they form color complexes, so those which cannot be explained by your valence bond theory. Now we are seeing, or we are examining those molecules through your crystal field theory. So crystal field theory, in crystal field theory we have discussed about your octahedral complexes, and this time we are discussing about your tetrahedral complexes. So the complexes is nothing but when there is a metal atom and there is ligands which are coordinate to the metal atom, they are forming bond, they are forming some chelates kind of thing, and they are forming coordination compounds. Okay, so which one will form your tetrahedral complex and which one will form your octahedral complex depends on the geometry or the way the ligand comes and approaches it, okay, and whether the ligand is a weak field or strong field ligands. So in tetrahedral complexes we will see tetrahedral complexes only with weak field ligands. There is no question of a strong field ligand to come and counteract or form a tetrahedral complex. Okay, so it will be only the weak field ligand, and it is approaching. We have discussed that now you will just imagine a coordination compounds in a three-dimensional form. Okay, so if you draw a three-dimensional axis, that is your x-axis, y-axis and your z-axis, and then if you put a metal atom in between some of the axis, and then if the ligand comes and approaches it through the direction of your dxy plane, dyz plane and dzx plane in this case, okay, it will come and form, as you know, tetrahedral angle is 109 degrees. So through 109 degree angle they will come and approach the metal atom, okay, and it will approach in dxy, dyz and dzx plane. And this time what happens, that in this time dz square and your dx square minus y square does not cause any repulsion. Only the repulsion takes place in which field? That is your T2G level. Okay, so T2G level or your dxy, dyz, dzx, they face the maximum repulsion because the ligand is approaching in their direction. Okay, so now this, in the tetrahedral splitting, what happens, the T2 level goes up due to repulsion, their energy increases and they form they go above the energy diagram. We will draw that in the energy diagram. They go above the axis, and then we draw the EG level or your dz square and dx square minus y square. There is no ligand approaching in their direction, so that time their energy becomes low. Okay, so and even the CFSE energy of tetrahedral complex is very much lower than your octahedral complexes. Okay, these things we will discuss how. So let us now first draw the just let me draw for you the energy diagram to explain the same. In your octahedral field we talked about your three-dimensional pictures, is it not? So here also we are talking about your three-dimensional pictures of coordination complex. Okay, so the metal ion will be somewhat in the middle of the plane. Okay, so there are three planes, that is your x-axis, there is your y-axis and that is your z-axis. Now in this case what happens is that, okay, so this way is your z-axis, this is your, so in this case in tetrahedral field what happens is that metal atom in between the axis, in x-axis and xy and your xz axis. Okay, as a result what happens are closer to dxy, dyz and your dxz axis, okay, which faces maximum repulsion. Dx square minus y square and your dz square orbital. Okay, so because of this dxy, dyz and your dzx, xy, dyz and dzx, these orbital, what happens is that they faces maximum repulsion. Okay, so they orbital are placed above above. Okay, and its energy is high. Okay. If you are drawing the energy diagram, first these are degenerate d orbitals. Okay, first, as the same is octahedral field, these field the energy will increase gradually as the ligand will approach. Okay, but here what happens is that your T2 level is at the higher one, T2G level is at the highest one, which is your dx y dy z, and your dz I explain. This is your dz square and dx square minus y square. So there is an energy difference. We know this is how much? This is 2 by 5 of delta t. Crystal field, we know this side is minus 3 by 5 delta t. Why? In case of your octahedral, what happens is that this side, because it is at the higher side, the x square and the x square minus y square, the energy difference here becomes delta naught, 3 by 5 delta naught. It becomes positive because this is upside, and now in this case this this T2 level is upside, whereas this is at the downside, so it will be minus 3 by 5. So this way delta t, so delta t is the crystal field splitting in your tetrahedral field. So this is your field strength. This is your tetrahedral field. So you have to write the same way on the octahedral field energy diagram, energy derivation, whatever I have done, it's the same way in the tetrahedral. So we are just showing you in this form. You can follow that video for extrahedral splitting. So this is your energy on this side. Okay, and this delta t is equal to 4 by 9 of your delta octahedral. Okay, remember this. This is the energy energy equation for a tetrahedral complex CFSE is 4 by 9th of your octahedral splitting, and it is always high spin complex. Okay, and there is no question of any low spin complex in tetrahedral field. For instance, delta t is less than your pairing energy. That means pairing energy is very much high in this case. Pairing energy means the energy which is required for the electron to pair up. So if in case of your octahedral field, when the ligand is a strong field ligand, that times what happens, the pairing energy occurs, and therefore EG level goes to the above, and then there is a T2G level is down. Whereas in this case, the pairing energy is very, very high. So your delta T is very less than your pairing energy. Question: why your crystal field splitting energy of tetrahedral is less than your octahedral? First answer to this is that because this ligand approaches in the direction of dxy, dyz, and dzx, so T2G level faces the most repulsion, and your EG level does not face any repulsion. So that's why we can say that the splitting of octahedral complex is